Good afternoon. My name is William Halliday. I work for Wildlife Conservation Society Canada, and today I'm going to be talking to you about our project on quantifying ship noise in the marine soundscape of the Western Canadian Arctic. Ship noise is pervasive in the marine soundscape worldwide, particularly near coastal cities and ports, as well as major shipping routes. The ship noise is caused by effectively any vessel that has a propeller or an engine, and that noise is created by for example, propeller cavitation or engine noise or any other sort of noisy activities on board. Close ships tend to create a lot of transient noise over tens of minutes, particularly in frequencies below 1 kilohertz, but can also create noises above 1 kilohertz, particularly when the ship is very close to, say, an acoustic recorder. Larger ships are also affecting ambient noise in the deep ocean, where ships hundreds of kilometers away are causing an increase in ambient noise level in the deep ocean, which has been shown over, as an increase of 3 decibels or more over the last few decades, per decade. The Arctic soundscape is defined by long ice-covered periods and short open water periods. It's a very complex soundscape that is shaped by sea ice, where the ice-covered season can be one of the quietest soundscapes in the world, especially under land-fast solid ice, where ice is effectively stopping the impact of wind on underwater sound levels. However, sea ice itself makes quite a bit of noises as it's breaking, as pieces come into contact with another, as the ice is deforming under extreme temperature changes. Ice can be quite noisy. However, during open water periods, the Arctic soundscape isn't that different from non-polar waters, where wind and rain tend to be the major drivers of underwater sound levels. The main difference is the amount of ship noise that's in the Arctic, which is much lower. Climate change, however, is causing a shift in the Arctic soundscape as sea ice is melting earlier and forming later in the year, leading to a larger open water period, which can also allow for more ship traffic. Ship traffic has historically been quite low in the Arctic. However, there have been a lot of recent increases due to the reduced sea ice and increased industrial activity. For example, the Canadian Arctic has seen a threefold increase over the last 3 decades. The increased ship traffic is by a variety of different things. Tourism destination, the Arctic as a shipping route, say from the Pacific to the Atlantic or from Asia to Europe, as well as industrial activities such as mines opening up or oil and gas activity leading to increased ship traffic. There are also future projected increases in Arctic ship traffic. Effectively, as the Arctic becomes more reliably ice-free, it will be a more reliable shipping route. Now, why is all of this important? Why do they care? Well, the Arctic is home to many unique species that have only been exposed to low levels of ship traffic and have evolved in this unique soundscape. Some Arctic species, such as beluga and narwhal, have been shown to be quite sensitive to noise, reacting to an icebreaker from as much as 50 kilometers away. And this is when sound levels are only just above ambient level. So understanding ship noise in the Arctic soundscape is an important part of the conservation of these Arctic species, given that we're expecting a continued increase in ship noise into the future. So for this study, we collected acoustic data. We've been collecting it since 2014 over a number of sites in the Western Canadian Arctic. This map shows the Beaufort Sea. This is the eastern Beaufort Sea. The left side of the map is effectively just past the Alaska-Canada border. And so all of these stars represent recording sites that we have. The furthest star to the right is also was recorded by our colleagues at Fisheries and Oceans Canada, who kindly provided data to be used in this study. So we have all of these recording sites. The color of the star represents the number of shipping seasons that they recorded for, so between 1 and 2 years. And in fact, we still have recorders out in the water that we'll be using for future studies of ship noise as well. The recorders were of 3 different types by Wildlife Acoustics. There's the Songmeter SM3M, that was a number of our earlier recorders. And then more recently, we've gotten into using sound traps by Ocean Instruments, the ST300 and the ST500s. Once we get the acoustic data back, we process it in a number of ways. First, using PAM guide software in MATLAB to calculate power spectral densities, as well as sound pressure levels and third octave bands, as well as other bandwidths. We also visually go through the data by creating spectrograms in Raven Pro and looking for ship noise signals, such as shown here on the right, The top is a smaller boat. The bottom is a large cruise ship. You can tell the difference between the two based on effectively the structure of their acoustic signals. So a large ship typically has a lot of low frequency tonals that are quite flat, whereas the small outboard engine creates these wavy sort of patterns across the spectrogram. But in both cases, at the closest point of approach, we see kind of a typical Lloyd's mirror pattern, that U shape in the figures as the vessel passes by its closest point of approach. We also have access to satellite AIS data, where we're able to quantify the distance to the recorders, between the ship and the recorders, as well as other relevant data from the ship, such as what ship it is, what type of ship it is, how big it is, and as well as what speed it's traveling at each point in time. This map here, or these maps here, show, for example, ship tracks going over our acoustic recorders. The top right one shows the recording near Cambridge Bay over a month. The bottom one shows all the ship tracks in 2020 going over our acoustic recorders. So compared to a non-polar region, that's not very many ship tracks, but it also means that we have a number of ships passing close by that we are able to measure in the absence of other ships for the most part. So one thing that we're doing here is looking at the prevalence of underwater noise from ships in our data. So here we've got some different figures. The ones on the right show sound pressure level in blue, and then the presence of ships within 10 kilometers of the recorder in orange. And you can see that the number of spikes in sound pressure level are related to ships coming close by. However, keep in mind that a lot of the variation in sound pressure level is also driven by variation in wind speed, as shown by the wind speed graph on the bottom left, and that correlates with the with 2017. So the data in the top right, and you can see that there were a number of very windy days, and that does correlate with a number of the peaks that happened in 2017. So that has to be taken into account in the analysis as well. However, the main point here is that there are a number of ships coming by the recorders, and that they are influencing sound pressure levels. Looking at the specific variables from those individual ships, such as distance or the number of ships close by, we are seeing some significant relationships. There are two distance figures here shown on the bottom, one from the Cambridge Bay site in the far east, and you can see there we've got sound pressure level in the 50 to 1,000 hertz bandwidth, and the distance to the ship in meters, and we're seeing a pretty decent relationship. It is a logarithmic relationship. The logarithmic relationship is shown as the curved line, whereas a linear relationship is shown as the solid straight line. We saw a similar pattern at our other site at Ulahaktak, which is a little bit further to the west from Cambridge Bay, which is shown on the bottom right. Again, as ships are getting closer to the acoustic recorder, sound levels are going up. Also, when we look at the number of ships close by, we're seeing an increase. So one ship, you see a slight elevation. Two ships, we're seeing even more. Three ships, even more than that. So, and these are just with ships within 10 kilometers, not necessarily super close to the recorder. Beyond this, we're also going and back calculating source levels on ships that are coming within 2.5 kilometers of the recorder. And we picked 2.5 kilometers because that's when the ship noise is typically filling up the entire spectrogram, a 5-minute by 3,000 hertz spectrogram, for example, where you can't see anything other than ship noise effectively. So to do this back calculation, it's based on the distance between the vessel and the recorder, accounting for frequency-dependent absorption in third octave bands or power spectral densities, and assuming a combination of spherical and cylindrical spreading using the 15 log R as the equation. And from this, we've been able to get a number of source level estimates so far. So on the left here, that's data compiled from 2 different recording sites in 2 different years. So not too many estimates, but a good number with a decent spread in how loud they are effectively. And then on the right is from another site where we have 2 years of data, and also with a number of source levels estimated. So the way the data are spreading out here, for example, on the left, that purple line is a vessel that was stopped effectively. So there's no propeller cavitation. All that noise is just from the engine effectively, and it has a much lower source level than all the other lines. On the right, this was the only data set so far that we've analyzed. It has really large ships, so tankers and bulk carriers, and those are the loudest ships that come through. So those are the green and orange lines up on that figure. And so those are much higher up than the smaller ships like tugs and research vessels and that sort of thing. And so when we break apart their broadband source level in the 50 hertz to 10,000 to 10 kilohertz range, we do see those large vessels really breaking apart from the smaller vessels, which is something that's seen in non-polar oceans as well, that the large ships are really the loud ones. They're the ones that are contributing the most to underwater noise levels. And so the large ships are shown in blue. Those are ships greater than 100 meters, and the smaller ships are in orange. Those are the ships less than 100 meters long. So that's what we've done to date. We now have another 2 full years of data that are fully processed, but we need to actually get into the analysis, pairing up the acoustic data with the satellite AIS data. One example is shown on the right here. That's our Cape Bathurst recorder, and these are all the ships coming within 10 kilometers of the recorder in blue, and then 2.5 kilometers of the recorder in orange. So the number of ships that are influencing the soundscape, and then the number of ships that we're going to be able to get source level estimates on. So we have 4 new deep water sites that we're expecting to get some greater propagation ranges on for different estimates. We're also going to expand the analysis to estimate distances of audibility between the ships and the acoustic recorder, as well as estimating propagation loss. So in conclusion, there are a relatively low number of ships at our recording sites, but that's also a good thing, both for the conservation of species, but also in terms of being able to record information on individual ships, which is something that's a little bit more difficult to do in non-polar oceans, where you just have tons of ships coming by a recorder at a time, and it's difficult to separate out what noise is from what ship. As ship noise becomes more prevalent part of the soundscape, understanding how different ships are contributing to the soundscape will continue to be important, which is why we're measuring the source levels of these ships that are in the Arctic. And with that, thank you so much for listening to my presentation. I need to acknowledge those who have provided data or helped with collection of data, such as people in the communities and our colleagues at Fisheries and Oceans Canada. Satellite AIS data from Meopar and Meridian through a partnership with Exact Earth, and funding from the Weston Family Foundation, Fisheries Joint Management Committee, and Transport Canada. Thank you.